आतुर प्रभु चरित्र सुनिले तो रसिया राम लखन सीता मन बसिया सूक्ष्म रूप धरि सियनि दिखावा विकट रूप धरि लंक चलावा भीम रूप धरि असुर समारे रामचंद्र के काज सवारे लाय यस जीवन लखन जियाए श्री रघुवीर हर विवर लाए रघुपति कीन्ही बहुत बड़ाई कहा भरत सम तुम प्रिय भाई सहस्र बदन तुम हर्ष गावे यस करि श्रीपति कंठ लगावे सनकादिक ब्रह्मादि मुनीसा नारद सारद सहित अहीसा यम कुबेर दिगपाल चलाते कवि कोविद कहि सके कहाते तुम उपकार सुग्रीव कीन्हा राम मिलाए राजपद दीन्हा तुम हनुमंत विभीषण राम तुम्हारे तुम रखवारे होत न आज्ञा बिनु पैठारे सब सुख रहे तुम्हारी सरना तुम रक्षक काहू को डरना आपन तेज सम्हारो आपे तीनों लोक हांकते कांपे भूत पिशाच निकट नहीं आवे महावीर जब नाम सुनावे नासई रोग हरै सब पीरा जपत निरंतर हनुमत वीर संकट से हनुमान छुड़ावे पराक्रम वचन ध्यान जोड़ावे सब पर राम राय सिर ताजा तिनके काज सकल तुम साजा और मनोरथ जो लावे तासु अमित जीवन फल पावे चारों युग प्रताप तुम्हारा है प्रसिद्धि जगत उजियारा साधु संत के तुम रखवारे असुर निकंदन राम दुलारे अष्ट सिद्धि नव निधि के दाता असवर दीन जानकी माता राम रसायन तुम्हारे पासा सादर तुम रघुपति के दासा तुम्हारे भजन राम को पावे जन्म जन्म के दुख बिसरावे अंत काल रघुपति पुर जाए जहाँ जन्म हरि भक्त कहाई और देवता चित्तन हरई हनुमत से ही सर्व सुख करई संकट हटई मिटई सब पीरा जो सुमिरई हनुमत बलवीरा जय 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 हनुमान गोसाई कृपा करो गुरुदेव की नाई सतवार पाठ कर जोई छूटहि बंदी महासुख होई जो यह पढ़े हनुमान चालीसा होई सिद्धि साखी गौरी सा तुलसीदास सदा हरि चेरा की जय माधव हृदय महाडेरा
प्रवाह भावितस्तरे घरेवलम्ब्य लम्बिताम्बुजङ्गमालिका ढमड्ढमड्ढमड्ढमन्निनादमड्ढमर्वयं चकार चण्डताण्डवं तनोतु नः शिव शिवम् जटाकटाः सम्भ्रमभ्रमन्निलिम्पनिज्जलिलोलवीचिवल्लरी विराजमानमूर्धनि धगद्धगद्धगज्ज्वलल्ललाटभट्टभावगे किशोरचन्द्रशेखरे रति प्रदक्षिणम् मम धराधरेन्द्रनन्दिनी विलासबन्धुबन्धुरा सुरद्दिगन्तसन्तति प्रमोदमानमानसे कृपाकटाक्षधोरणी निरुद्धदुर्धरापदि क्वचित् दिगम्बरे मनोविनोदमेतु वस्तुनि जटाभुजङ्गपिङ्गळस्फुरत्फणामणिप्रवाहदम्बकुङ्कुमद्रवप्रलिप्तदिग्वधूमुखे मदान्तसिन्धुरस्फुरत्पगुत्तरीयमेधुरे मनोविनोदमद्भुतं विबद्धु भूतभर्तरी ॐ नमः शिवाय सदाशिवं भजाम्यहं सदाशिवं भजाम्यहम् ॐ नमः शिवाय सहस्रलोचन प्रवृत्य शेषलेखशेखर प्रसूलधूलितोरणि विदूसराङ्घ्रिपीठम् भुजङ्गराजमालया निबद्धजाढजूटक श्रियै चिराय जायतां चकोरबन्धुशेखर ललाटजन्मरज्ज्वलद्धनञ्जय स्फुलिङ्गभावितीतपञ्चसायकं नमामि लिम्बनायकं सुधामयूखलेखया विराजमानशेखरं महाकपालि सम्पदे शिरोजटानमस्कृता करालभालभट्टिका दगद्धगद्धगज्ज्वलद्धरञ्जय धनञ्जयाहुतीकृत प्रचण्ड पञ्चसायके हराधरेन्द्र नन्दिनी कुचाग्र चित्र पत्रकार कल्पनैक शिल्पिनी त्रिलोचने रचिर्मम नवीन मेघमण्डली निरुद्ध दुर्धर स्फुरत् भूनिशीतिनी धम प्रबन्ध बद्ध कन्दर निलिम्ब निर्झरीधरस्तनोतु कृत्ति सिन्धुर धरानिधान बन्धुर श्रियं जगद्गुरन्धर प्रफुल्लनीलपङ्कज प्रपञ्चकारिमप्रभावलं विकण्टकन्दली रुचिप्रबद्धकन्दरं स्मरच्चिदं पुरच्चिदं भवच्चिदं मखच्चिदं गजच्चिदान्धकच्चिदं तमन्तकच्चिदं भजे अखर्व सर्वमङ्गला कलाकदम्बमञ्जरी रसप्रवाहमाधुरी विजृम्भणा मधुव्रतं स्मरान्तकं पुरान्तकं भवान्तकं मखान्तकं गजान्तकान्तकान्तकं तमन्तकान्तकं भजे स्फुरत्करालभालव्यवानिमित्तिमित्तिमित्त्वनं मृदङ्गतुङ्गमङ्गल परिक्रम प्रवर्तित प्रचण्ड ताण्डव त्रिशक्तिचक्रकल्पयोर्भुजङ्गमौक्तिकस्रजोलरिष्टरत्नलोष्टयोः सुहृद्विपक्षपक्षयोः धरारविन्दचक्षुषो प्रजामहि महेन्द्रयोः समप्रवृत्तिकक्कटा सदा शिवं भजाम्यहम् सदा शिरस्तमञ्जलिं वहति लोल लोल लोचनो ललाम बालरत्नका शिवेति मन्त्रमुच्चरन् कदा सुखी भवाम्यहम् इमं हि नित्यमेव मुक्तमुत्तमोत्तमं स्तवं पठन् स्मरन् भुवन्धरो विशुद्धिमेति सन्ततं हरे गुरौ सुभक्तिमाशु याति नान्यथा गतिं विमोहनं हि देहिनां सुशङ्करस्य चिन्ता विमोहनं हि देहिनां सुशङ्करस्य चिन्ता
related to C as per the relations. So pictorially, if you have say A is related to a set of various set theoretic operations which we can perform on relations. Specifically, we will be discussing on the powers of a relation and closure of a relation. So it turns out that since relations are nothing but a set, but so we can perform various set theoretic operations like union, intersection, set difference on relations as well. So to demonstrate this, let's consider two relations R1 and R2. You have a relation R1 which consists of all x, y pairs or all real numbers x, y where x is less than y. So here my relation R1 is defined over the set of real numbers, my relation is the set of real numbers. So R1 will have all tuples in the form x, y where real number x is less than real number y. And similarly, my relation R2 is another relation defined over the set of real numbers consisting of all x, y pairs where the real number x is greater than the real number y. Now, if I take the union of these two relations, and the union of these two relations is well defined because both R1 and R2 are sets, and we can perform the union of these sets. So it turns out that the union of these two relations will have all pairs of the form x, y, where the real number x is not equal to real number y. Okay, because the union will have all the elements of R1, and the union also will have all the elements of R2. So one way of describing the union of these two relations is that it have all x, y pairs where either x is less than y or x is greater than y. But if we want to represent the same, if we want to state the same thing in a compact way, we can say that it has all x, y pairs where x is different. Whereas if I take the intersection of these two relations R1 and R2, then it turns out to be a set because you can't have real numbers x and y where x is simultaneously less than y as well as x is simultaneously greater than y. So you can't have any x, y pairs satisfying simultaneously the conditions for the relation R2. In the same way, it's easy to see that if I take the difference of the relation R1 and R2, if I subtract R2 from R1, then I will be getting the relation R1. Only it will have only the elements of the form x, y where x is less than y. And similarly, the difference of R2 minus R1 will be the relation R2. Now we can perform another interesting operation on the relations which is called as composition of relations. So imagine you are given two relations R and S. The relation R is from the set A to B. So R is a subset of A cross B. Okay, and your relation S is from the set B to C. So S is a subset of B cross C. Okay, I am taking here three arbitrary sets A, B, C. A, B, C may be same, they may be different. There is no relationship. They are just arbitrary sets here. Okay, and I am naming the elements of set A as A1 to AL. Similarly, the elements of B are named as B sub 1 to B sub M, and elements of C are named as C sub 1 to C sub M. Okay. Now, the composition of these two relations is defined as follows. So first of all, we use this notation SOR. Okay, and this means that I am going to apply the relation R first and then the relation S. Okay, so it's not the relation S applied first and then the relation R. We are going to apply the relation R, and on top of that, we are going to apply the relation S. Okay, so this will be a relation from the set A to C. Okay, and that's why this ordering matters a lot. So if I am saying S composed with R, so this operation O is called as the composition operator. And right now I am composing the relation S with the relation R. If I write ROS, then that's a different relation. That means I am composing the relation R with the relation S. That means here S will be applied first, and on top of that the relation R. So the notation specifies clearly which relation is composed with which relation. So this S composition R will be a relation from the set A to C. That means it will have pairs of the form, ordered pairs of the form A, C. And the definition here is it will have all ordered pairs of the form A, C, provided you have some element B, small b in the set big B such that A is related to B as per the relation R and B is related to C as per the relation C. So pictorially, if you have say AI related to Bj as per the relation R, so the notation specifies clearly which relation is composed with which relation. So this S composition R will be a relation from the set A to C. That means it will have pairs of the form, ordered pairs of the form A, C, and the definition here is it will have all ordered pairs of the form A, C, provided you have some element B, small b in the set big B such that A is related to B as per the relation R and B is related to C as per the relation C. So pictorially, if you have say AI related to Bj as per the relation R and the same Bj is related to Ck as per the relation S, then we will say that AI is related to here it's Ck. AI is related to Ck as per the relation S composition R. Okay, so it's some kind of transitive property here, that transitive pairs or transitive tuples of the A comma C, which we will be including in the relation S composition R. Okay. So once the definition of compositions of relations is given, we can define what we call as powers of a relation. And how it is defined? So imagine R is a relation from A to B. That means R is a subset of A cross B. Then the definition of powers of a relation is as follows. So R power 1 is defined to be the relation R itself, and then recursively I define the n plus 1th power of R to be the composition of the relation which is nth power of R with the original relation. So again I stress here the important order matters here. The n plus 1th power is defined to be the composition of R power n with R. That means you have to apply the relation R first, and then you have to apply the relation R power. It need not be equal to the composition of R with the nth power of R. That may or may not be the case, because in general the composition of two relations need not be commuted. That means you have, so again plus 1th power of R is as follows. Then the definition of powers of a relation is as follows. So R power 1 is defined to be the relation R itself, and then recursively I define the n plus 1th power of R to be the composition of the relation which is nth power of R with the original relation R. So again I stress here the important order matters here. The n plus 1th power is defined to be the composition of R power n with R. That means you have to apply the relation R first, and then you have to apply the relation R power. It's not equal to, it need not be equal to the composition of R with the nth power of R. That may or may not be the case, because in general the composition of two relations need not be commuted. Okay. So let me demonstrate the powers of a relation with an example. So here I have defined a relation R consisting of the pairs 1, 1, 2, 1, 3, 2 and 4, 3. So R power 1 as per my definition will be the relation R itself. Now R square will be the composition of R with R. And my claim is that R square will consist of these four pairs. Why so? So let's start with 1, 1. So you have 1, 1 present in R, and the same 1 is again related to 1 itself as per R. Therefore I can say that transitively, so this is your A here, this is your B here, and this is your B here, and this is your C here. So as per the definition A comma C should be there in R square. That's why 1, 1 will be present in R square. Okay. Now take the tuple 2, 1. So this is your A comma B, and you have the tuple 1, 1 also present in R. This is your B comma C. So therefore A comma C should be in R. R square. That means 2, 1 will be in R square. If you take 3, 2 present in R, Okay, so this is your A, this is your B, and you have 2 comma 1 present in R orbit as well. This is your B, this is your C. Therefore, A comma C, namely 3 comma 1, will be in R square. And in the same way, you have A comma B here, namely 4 3, and B comma C here, namely 3 2. That's why 4 comma 2, which is A comma C, will be present in R square, and no other tuples will be there in R square. Okay. That's how we take the powers of relation. If I want to compute R cube, then it will be the composition of R square with the relation R. So I will take this R square here first and compose it with the original relation. That means the relation R has to be applied first, and then on top of that the relation R square has to be applied. Okay. So for instance, this is your AB here present in R, and you have B. C as well present in R square. Therefore, AC, which is 1 comma 1, will be present in R cube. Similarly, 2 1 is present in R. You have again 1 1 present in R square, so that's why 2 1 is present in R cube. You have 3 comma 2 present in R, and 2 comma 1 is present in R square, so that's why you will have A comma C, which is 3 comma 1 here present in R cube. You have 4 comma 3 present in R, and you have 3 comma 1 present in R square, so that's why 4 comma 1 is present in R cube. And similarly, if you take the R power 4 relation, then it turns out to be the same as R cube. And now you can check yourself that after the fourth power, you take any power of the relation R, it's going to give you the same relation as R cube. You won't get any new tuples added in the relation in the next powers of R. Now, next, what we are going to discuss is a very nice interpretation of the powers of a relation in terms of a property in the corresponding graph. So imagine you are given a relation over some set A consisting of n elements, and suppose the relation is represented by a directed graph G. Now, the claim here is the following: the ordered pair AI AJ will be present in the mth power of the relation, namely AI is related to AJ in the mth power of the relation if and only if there is a directed path of length m from the node AI to the node AJ in the digraph of your relation. Okay. So what do I mean by directed path here? So remember, G is a graph where you have vertices A1, A2, AI, AJ, AN, and you have directed edges. So if there is a direct edge between two nodes, from one node to another, say from A1 to A2, then this will be considered as a directed path of length 1. Whereas say if you have a path of the form from A2 you have an edge to A1, and from A1 you have an edge to AN, then I will say that the path A2 to A1, then I will say that the sequence of edges A2 to A1 and A1 to AN, this will be considered as a directed path of length 2 from A2 to AN. Right. Like that, you can imagine a directed path of length m from AI to AJ. That means your source or the starting point will be AI, the end point will be AJ, and intermediate, and you will have m number of intermediate directed edges. Okay, in that path. Right. That's the interpretation of a directed path. Later on, when we will discuss graph theory in detail, we will formally define what exactly is a path, path length, and so on. Right. But right now, we want to prove this nice theorem regarding the power of a relation. And since this is a universally quantified statement, because even though the universal quantification is not explicitly available here, but the statement is for all m greater than equal to 1. So that's why we will use a proof by induction on the power m to prove this theorem or the property, and the base case will be m equal to 1. And the statement is of course trivially true for the base case, because if at all AI is related to AJ in R, that means that there will be a direct edge from the node AI to the node AJ in my graph. That comes from the definition of the diagram. So the base case is trivial to prove. Now assume that my inductive hypothesis is true. That means I assume that the statement is true for n equal to k. By that I mean that if AI is related to AJ in the kth power of the relation, then there exists a direct path. There exists a directed path, not direct path. There exists a directed path of length k starting at AI and ending at AJ in the graph G. Okay. Now I go to the inductive step and I consider an ordered pair, an arbitrary ordered pair in the k plus 1th power of the relation. So suppose the ordered pair AI AJ is present in the k plus 1th power of the relation, and the k plus 1th power of the relation is basically the composition of R with the kth power of the relation as per the definition of powers of the relation. Now, when can it be possible that AI is related to AJ in the k plus 1th power of the relation? That is possible only if the following two conditions hold. There should be some element A such that AI is related to A, and that element A should be related to AJ. Then only I can say that AI is related to AJ in the k plus 1th power of the relation. But AI related to A means there is a structure of this form in your graph. Namely, there is a direct edge from AI to A. But it should not be a dotted arrow, it should be actually a straight arrow, because indeed I have a direct edge from AI to A. And the interpretation of A being related to AJ in the kth power means I have a directed path of length k starting at A, ending at AJ. This comes from my inductive hypothesis. Now, what can I say regarding a path from AI to AJ? I can say that if I concatenate these two paths, that means if I take the edge from AI to A first, and then once I reach the node A, from there I traverse through this path and come to the node AJ. That will give me a path starting with AI, ending with AJ. And now what can you say about the length of that path? The length of that path will be k plus 1. That means I have shown here that if the ordered pair AI AJ is present in the k plus 1th power of the relation, then in the directed graph of your relation, you indeed have a path of length k plus 1 starting at AI, ending at AJ. Next, let's define what we call a closure of a relation. So what do we mean by this? So imagine you are given a set A, okay, that may be finite or infinite, and you are given a relation R over the set A. That means the relation R is a subset of A. And I have some abstract property P. It is some abstract property. And I am interested to check whether the relation R over the set A satisfies this property P or not. If it satisfies the property, well, good. But that need not be the case. R that is given to you need not satisfy the property. So the closure of the relation R is defined with respect to this property P. Okay. So if you change the property P, the closure will change. So what exactly is the closure of the relation R with the property P? Well, it's the smallest superset of R which has the property P. So pictorially what I am trying to do here is I am trying, if my relation R already satisfies the property P, I don't need to add anything to the relation R. I don't need to add any extra element to the relation R to satisfy the property P. But if my relation R does not satisfy the property P, then I will be interested to introduce new ordered pairs in the relation R and convert it into another relation S so that the expanded relation S satisfies the property P. That's what I'm trying to do here. So this S you can imagine as expanded version of R. And this S is also going to be a relation over set A itself. I am including the original relation R that is carried as it is. On top of that, I may add few extra elements and try to ensure that the expanded R, which is S, satisfies the property P. But I am not going to do the expansion arbitrarily. I am interested in the least possible expansion. Least expanded. What I mean by least, that means this is the minimal expansion which I need to do in order to ensure that the relation S satisfies the property. That's important. Otherwise, what's the big deal in expanding the relation R? You keep on adding any arbitrary number of elements, definitely you will more or less soon get an expanded version which will satisfy the property. So we are interested in the smallest possible expansion. So let's see some examples of this abstract property P and how the resultant closure looks like. So my first abstract property is the reflexive property, and this gives us what we call as reflexive closure of a relation. So you are given a relation R over the set A, and I am interested to see whether this relation R satisfies the reflexive property or not, reflexive over the set A. Okay. So that's what is the reflexive closure of the relation R. So how can you construct a reflexive closure of R? Well, you just take the union of R with all ordered pairs of the form AI, AI, where AI is present in your set big A. If your AI, AI is already there in the relation R, then as per the union definition, you will not be including it again. Remember, union means if AI, AI is present in R as well as in this new set, new relation, right? So this new relation, I'm calling it as delta relation. So this delta relation, you can imagine, it is consisting of all ordered pairs of the form AI, AI, such that AI is present in A. So if AI is already there in R, it will not be included again. But if AI is not present in R, then due to the union, due to taking union with this delta, it will be now added to the relation R. And now you can see that this is your expanded R. Okay, that may be same as R itself. In case if your relation R is already reflexive, then you are not going to add any extra elements. Okay, so this expanded R will have the original elements of the relation R plus this expanded R will satisfy the reflexive property. Okay. Now let's take the case when my abstract property P is the symmetric property. So again, I am given a relation R defined over the set A, and I am interested to form a symmetric closure of R. Why I am calling it closure? Because I am trying to put a layer over and trying to enclose the original relation R and get a relation which has the original R as well as it satisfies the property. That's why it's called a closure. Right? So how do I form the symmetric closure? So if you recall the property of a symmetric relation, then the requirement here is that if A, B or if AI, AJ is present in R, then I need the guarantee that AJ, AI should also be present in R. Right? This is the requirement from a symmetric relation. So, and I need to include the original relation R. So what I'm going to do is, I'm going to take the union of R with what I call as the inverse of the relation. This is the inverse relation. And what is this inverse relation? It is defined to consist of all ordered pairs of the form AJ, AI such that AI is related to AJ in the original relation. Okay. So if in your original relation AI is related to AJ, then in the R inverse relation AJ will be related to AJ. And it's easy to see that if you take the union of R with its inverse, then the resultant relation will be symmetric and it will have the original relation R, and this will be the smallest possible expansion of your relation R which satisfies the symmetric property. Okay. Now what about the transitive closure? So relation R which satisfies the symmetric. AI is related to AJ, then in the R inverse relation AJ will be related to AI. And it's easy to see that if you take the union of R with its inverse, then the resultant relation will be symmetric and it will have the original relation R, and this will be the smallest possible expansion of your relation R which satisfies the symmetric. Okay. Now what about the transitive closure? So it turns out that finding transitive closure is not that simple. Why so? So let me demonstrate that with an example. So you might say that intuitively to find the transitive closure, I keep on I add all elements of the all ordered pairs of the form A, C such that, again sorry for the typo here, such that A is related to B as well as B is related to C in the relation R. Because only when I add such ordered tuples of the form A, C in the relation R, it will ensure that the transitive property is satisfied. So let's try to do that. you are given the original relation R, and I'm taking the union of the original R, and I'm adding all the ordered pairs of the form A comma C which are needed to ensure the transitivity property. So for instance, I need to add 1 comma 2. If you are wondering why I need to add 1 comma 2, because I have A comma B present here, I have B comma C present here, so I need A comma C which is 1 comma 2 also to be present, which is not there in R. So I say let me add it. In the same way, I have 2 comma 1 present, which is your A comma B, and you have 1 comma 3 also present, which is B comma C. So you should add 2 comma 3 and so on. So these are the new things which I add, and my R prime will be this new relation. Okay, it has my original relation R, but now let us stop here and ask whether R prime is transitive or not. It turns out that R prime is not transitive, right? So for instance, you have 2 comma 3 present here, which is your A comma B, and you have 3 comma 2 present, but you don't have A comma C, namely 2 comma 2 present in the relation R prime. So even though you have expanded R and got R prime, your R prime is not satisfying the transitivity relation property. So what you can do is you can again apply the rule. And to apply the rule, what I do now is I take the union of R prime, namely the expanded R, and add all the extra ordered pairs of the form A comma C which were missing in R prime to satisfy the transitivity property. So see, I'm adding 1 comma 1 here. Why I'm adding 1 comma 1? Because I have AB here and BC here, but AC, namely 1 comma 1, is not present in R prime. So I am adding here, and so on. And now I call this expanded relation as R double prime, and now you can check that this R double prime is indeed satisfying the transitivity property. So if you see closely here, what happened in this whole process is the following. First time when I expanded the relation R, I took the union of R with all the tuples which will be present in R square. You can verify that as per our definition of R square, the tuples which I have highlighted here are nothing but R, which are the tuples in R square, are the tuples in R square. Sorry. So the tuples which I have highlighted here, and I have added with the tuples which are present in R are nothing but the tuples of R square. In the same way, when I expanded R prime to R double prime, the tuples which I added actually are nothing but elements of R cube, and we call R cube is nothing but R square composition R. So it turns out that when we want to find a transitive closure, it need not be a one-step process. I need to apply this rule, namely keep on adding the ordered pairs of the form AC such that AB and BC are there in your expanded relation, and I may need to keep on applying this process several times, and then only I can obtain the transitive closure. So that brings me to the end of this lecture. Just to summarize, in this lecture we introduced some set theoretic operations on relations, and we discussed the various closure properties with respect to a given relation. Thank you. Hello everyone, welcome to this lecture. In this lecture we will continue our discussion regarding how to construct a transitive closure of relations, and for that we will see some graph theoretic interpretation of transitive closures. We will discuss what we call as the connectivity relationship in the graph of a relation, and then we will see a naive algorithm for computing the transitive closure. So let me start by introducing the connectivity relation. So imagine you are given a relation R over a set which may or may not be finite. So your R is a subset of A cross A, and I define this relation R prime, R star, which I call as the connectivity relation, and this is basically defined to be the union of different powers of your relation R. Okay. Relation R over a set producing the in the graph of a relation. Let me given a relation R over a set which may or may not be finite. So your R is a subset of A cross A, and I define this relation R prime, R star, which I call as the connectivity relation, and this is basically defined to be the union of different powers of the relation R. Okay. It turns out that as per my definition of R star, an element AI will be related to AJ in this relation R star, provided there exists some path of any length. It may be of length 1, it may be of length 2, it may be of length 3, I don't care about the length. The guarantee is that there exists at least one path from the node AI to the node AJ in the directed graph of your relation R. And why so? Because recall in the last lecture we proved this theorem by induction, right? We proved this statement by induction. The statement states that if you have element AI related to element AJ in the nth power of your relation R, then that's possible only if you have a path of length n from the node AI to the node AJ in the directed graph of your relation R. Now if I say that AI is present in R star, then it means that either AI comma AJ is present in R power 1, or it is present in AI, it is present in R power 2, and in the same way it will be present in some power of I don't know which power, but since it is present in R star, and the definition of R star is that it's a union of all powers of R. So if AI is related to AJ in R star, that means it is present in one of these powers of R, say if ith power. Then, as per this theorem statement, which we have proved in the last lecture, there exists a path of length I from the node AI to AJ. It might be possible that AI, AJ is also present in, say, some other power of R. That's also possible. Say it's present in the kth power. That means, as by the same statement, there exists a path of length k from the node AI to AJ. So that's why I am not focusing on the path length here. I'm just stating here that if at all the element AI is related to the element AJ in the relation R star, then some path exists from the node AI to the node AJ in your graph of the relation R. Okay. Now we will be focusing on this connectivity relation, where the relation R is defined over a finite set. That means R is defined over a finite set consisting of n elements. My claim here is that R star is nothing but the union of R square and up to R power n, because you don't need to take the union of higher powers of R. Any higher powers of R will be subsumed in the union of the first n powers of R, provided your relation R is defined over a finite set consisting of n elements. And this is because what can be the maximum path length between any two nodes? Remember, in the graph of your relation R, you have n nodes, because now the relation is defined over a set consisting of n elements. Okay. So what can be the maximum path length? The maximum path length can be n only. Okay, because you have only n distinct nodes possible. Of course, you can keep on traversing along this path again and again and again. That will be considered as a path of a higher length. But what do I mean by maximum path length? By maximum path length, I mean here maximum path length where path has distinct edges. And why distinct edges? Because if I say, for instance, consider R power n plus 1, that means I am interested to find out whether there exists a path of length n plus 1 between any two nodes in the graph G. Well, since I have only n distinct nodes possible, then the path of length n plus 1 is possible only if a node is repeated in the path. That means, say, for instance, I have a path of, say, n is 3. Okay. Now say n equal to 4. Say. Okay. So I can say path of length 5 exists between A1 to A2, because I can go from A1 to A2, that's 1, and A2 to A3, that's 2, then A3 to A4, that's then 3, and then A4 to A1, that's 4, and then again from A1 to A2, that's length 5. Okay. But the same path can be considered as a path of length 1 because you have the node A1 to A2. So what I can say is that both A1, A2 will be present in the relation R, and the same A1, A2 will also be present in R power 5. The same A1, A2 will also be present in R power 9, and so on. So when I will be constructing R star, which will be union of R and R4, then anything which is present in R power 5, R power 9, and so on, so for instance this element A1, A2 which is present in R power 5, R power 9 would have been already subsumed in R itself. I don't need to separately consider those pairs by considering the fifth power of R and so on, because I know that I can't have a path of length 4 consisting of more than 4 consisting of distinct edges. If at all there is a path of length more than 4, that means some edges and nodes are repeated. That means that path, by excluding the repeated edges and nodes, would have been already counted in some lower power of R when I would have constructed R star. So that's why when my relation R is defined over a finite set consisting of n elements, then to construct a connectivity relationship, I just need to focus on the first n powers of relation R. There won't be any extra ordered pairs beyond this n different powers of relation R which are present in R star. Okay. So we have not proved in details, but intuitively this is the statement. So now what we are going to prove here is, now we are going to see a relationship between the transitive closure and the connectivity relationship. So remember, in the last lecture we saw an example where we constructed the transitive closure of a relation, and there we iteratively apply the process, the rule that if you have A, B and B, C in the expanded relation R or in the original relation R, then you add the element A, C, and you keep on doing this process till you don't need to add any extra elements of the forming process. So now what we are going to do is we are going to formalize that process by stating this beautiful result that the transitive closure of the relation R is nothing but the connectivity relation. Now to prove this theorem, we need to prove several things. The first thing that we have to prove is that the relation R, the original relation R, is present in your R star, because that's one of the requirements of transitive closures, that your original relation should be present in the closure of that relation. But it's easy to see that the original relation R will be a subset of R star. because R star is nothing but R union the higher powers of R. So your original R will be definitely present in R star. So all the ordered pairs which were there in R will be present in R star. The second thing that we have to prove is that indeed this expanded relation R, which is R star, is satisfying your transitivity property. And for proving that this relation R star is going to satisfy transitivity property, what we are going to do is we are going to show the following. We take any arbitrary A, B and B, C which are present in R star, then you have the guarantee that A, C is also present in R star. Why I am going to show it for arbitrary AB and arbitrary BC? Because the property of transitivity property is the transitivity relationship. The demand is that for all ABC, if AB and BC are here in a relation, then you need AC to be in a relation. And this need to be shown for all ABC. But we can't take every possible ABC in R star and show this implication to be true. So that's why we are going to show it for arbitrary AB and arbitrary BC and then take the help of universal generalization and conclude that the statement is universal for all elements of that. So assume to prove this implication, we have to show that the left hand side or the premise of this implication is true, and then we have to show that even the conclusion is true. That's how the definition of implication is, right? So assume that AB is present in R star. That means as per the definition of R star, AB is present in some power of R, say the jth power. Because that's the definition of R star. And in the same way, imagine that BC is present in R star. That means it is present in some power of R, say the kth power. There will not be any relationship between J and K. It will be anything K equal to anything. So what I can say here is that the tuple A, C will be present in the J plus kth power of R, because that's the definition of J plus kth power. Because the J plus kth power will be nothing but the J plus kth power of R will be nothing but R power K composed with R power J. That means you would have applied the relation R power J first. That means you will say that say AB is there in R power J, and on top of that you will apply the relation R power K. So here B is acting as your intermediate element. So AB is present in R power J and BC is present in R power K. Hence you will conclude that AC is present in the J plus kth power. And J plus kth power R power J first. That means you will say that say AB is there in R power J, and on top of that you will apply the relation R power K. So here B is acting as your intermediate element. So AB is present in R power J and BC is present in R power K. Hence you will conclude that AC is present in the J plus kth power of R. And J plus kth power of R will be included in R star, because that's the definition of R star. So we proved this implication to be true for an arbitrary ABC. That shows that the relation R star is transitive. So we have shown two of the requirements of transitive closures are satisfied by your R star relation. Now we have to prove the important thing. We have to prove that R star is the smallest possible expansion of your relation R, which is transitive. And the way we are going to prove this is as follows. We have expanded our relation R to R star. We have shown that R is present in R star, and we have also shown that R star is transitive. Now we have to show this third property. How we are going to do this? We will do this by showing that you take any transitive relation which includes R. That means you take any expanded version of R which is transitive. In that expanded version of R, when you S, R star is present. Okay, that will automatically show that R star is the smallest possible. That means there is no smaller subset of R star which includes R as well as it is transitive. That's what we are proving here pictorially. That means it's not that S is present in R star. That's not going to happen. We are going to prove it other way around. We are going to show that you take any transitive relation which is expansion of R star will be definitely present in that expansions. And that automatically will show that R star is the smallest expansion that you do. So formally we have to prove that you take any set S, any relation S which is a transitive relation such that R is included in S, then the expanded R, namely the connectivity relation, is included in this expanded relation S. So to prove this property, we are going to take help of a very small fact regarding the transitive relations, and that fact is the following. My claim here is that if S is a transitive relation, then you take any power of that transitive relation, it will be a subset of the original relation. And since this is a universally quantified statement for all n greater than equal to 1, we can quickly prove it by induction. The base case is obviously true because S is always a subset of S. Let the statement be true for n equal to 1 to k, and now we are going to prove it for n equal to k plus 1. So imagine you have an arbitrary AC element A comma C present in the k plus 1 power of S. And as per the definition of S power k plus 1, you have some intermediate element B such that A is related to B in the relation S and B is related to C in the relation S power k. Then I apply the inductive hypothesis here. Since B comma C is present in S power k and the statement is true for n equal to 1 to k, that means this B comma C is present in S as well, because S power k is a subset of S as per my inductive hypothesis. So now if I have AB present in S and BC present in S, right, I can say that AC is also present in S, because my base case or the hypothesis of the statement that I am proving is that S is transitive. Okay. So this is a very straightforward fact regarding the transitive relations. If your relation is transitive, you take any subset of that, any power of that relation, it will be always included in your original relation. Okay. So we have proved it for all n greater than or equal to 1. Now I apply the definition of S star. What is S star? S star is going to be S power 1 union S power 2 union S power n union higher power of anything. So each of these powers is included in the relation S, because that's what we have proved. We have proved for all n greater than or equal to 1, origin is going to retain here. Now coming back to the statement that we want to prove here. We want to prove that if you take any transitive relation which is an expansion of R, then the connectivity relation of R is included in that, is going to be included in that expanded R. Okay. So we have to prove this subset relationship property. So the definition of subset is that if you have any A comma B present in R star, I have to show the same AB is present in S as well, provided the hypothesis of the subset of S square. That also means R cube, whatever is present in S star, it is bound to be present in S as well, right? And R star is defined to be union of different powers. So to interpret the connectivity relationship in terms of the directed graph representing the relation, what I can say is that AI is related to AJ in this connectivity relationship if AJ is reachable from AI by some path, right? Because AI comma AJ present in R star means it is present in some power of R, say that power. That means I have a path of length n from the node AI to the node AJ. That's what we have proved. Abstractly, we can, for instance, imagine A is the set of all computers in the university, and I define a relation between the computers as follows. I will say that computer AI is related to computer AJ if there exists a direct link between computer AI and computer AJ. That means AI can directly send a message to the computer AJ by the channel or the cable through which the computer AI is connected to computer AJ. Then if I construct the connectivity relation R star for this given relation R, then it's easy to see that R star will have all ordered pairs of the form AI comma AJ, where AI is connected to AJ, maybe directly or through intermediate computers. That means R star basically talks about all interconnected computers in your university. Now let me give you another example of this connectivity relationship. So have you ever wondered that how Facebook computes new friend suggestions? So imagine A is the set of all Facebook users, and I define a relation between two Facebook users as follows. I call that relation as R. I say that user AI is related to user AJ, provided AI and AJ are mutual friends of each other, mutual friends over Facebook. Okay. Now, if you take the relation R star with respect to this R, then with the connectivity relationship defined over the relation R over the Facebook users, then if you have AI related to AJ or AK in the relation R star, that means I can say there are a sequence of intermediate Facebook users such that AI is related to the first user, then the first user is related to the second user, and so on, and the second last user is related to AK. That means in terms of a graph theoretic property, you can interpret that there is a path of some length from AI to AK, right? That means even though AI and AK may not be mutual friends, what Facebook can think is that it might be the case that AI has not searched for the Facebook user AK and vice versa. So let's send a suggestion to AI that, well, you know the user AK or not, and similarly to the user AK, right? Because AI is directly related to some A, the user A is related to user B, the user B is related to user C, and say by sequence of intermediate users, you have AI related to AK. And since friendship is by default considered to be transitive. And of course, there might be exceptions as well where A is represented with B and B is represented with C, but A will not be represented with C. That's why Facebook just gives you a suggestion that, hey, looks like that we have found someone who is related to you by some intermediate users. And that's how. And to do that, basically, the Facebook algorithm has to construct here the connectivity relationship of this relation. Okay, so this connectivity relationship has got a huge amount of significance. Now the question is how we algorithmically compute this connectivity relationship. So we will be focusing on the case when the relation is over a finite set, and recall that in this case R star is nothing but the union of first 10 powers of R. So what we are going to construct is, we are going to construct the Boolean matrix MR star. So it will be an n-cross-n Boolean matrix representing your connectivity relation R star, where the ith row in the jth column will be 1 provided the element AI is related to AJ in the connectivity relationship R star. So the question that we want to address here is that you are given the original relation R, namely the Boolean matrix representing the relation. Now the question is how connectivity relationship of this relation. Okay, so this connectivity relationship has got a, but will not be sent with C. That's why Facebook just give you a suggestion that, hey, looks like that we have found someone who is related to you by some intermediate user. And that's how connectivity relation R star, where the ith row in the jth column will be 1 provided the element AI is related to AJ in the connectivity relationship R star. So the question that we want to address here is that you are given the original relation R, namely the Boolean matrix representing the relation R. How you compute the Boolean matrix representing the relation R star, where the relation R is defined over a set consisting of n elements. So here is the naive algorithm for computing the matrix for connectivity relation. We compute the matrix for different powers of relation R. So we are already given the relation for R. We are already given the matrix for the relation R, so we don't need to compute that. So that's why for I equal to 2 to n, we compute the matrix for the next powers of R. And this we can compute by performing a Boolean matrix multiplication operation, which I will discuss very soon. And here what I am going to do is to compute the matrix for the ith power of the relation R. I am going to multiply the matrix for the original relation along with the matrix for the I minus 1th power of the relation R, provided I have already computed it. And then what I am going to do is, I am going to take the Boolean disjunction of the individual n cross n matrices for the different powers of R that I have computed, and that will help me to get the Boolean matrix for this connectivity relation R star. So now there are two operations here, the Boolean matrix multiplication and the disjunction operator. So now there are two operations here, the Boolean matrix multiplication and the disjunction operation. So I'm going to say the Boolean matrix multiplication and the disjunction operation. So two operations here, the Boolean matrix multiplication and the disjunction operation. So I'm going to define them one by one. So let's start with this Boolean matrix multiplication here. So the goal here is the following. You are given the relation R, or equivalently its matrix representation, and say you have already computed the matrix representation for the I minus 1th power. And now your goal is to compute the matrix for the ith power of the relation R. So recall, as per the definition of the ith power of the relation R, AI will be related to AJ if you have AI related to some AK in the relation R, and AK is related to AJ in the relation R power n minus 1. That's what is the definition. Okay, so that's what pictorially I have written. If that's the case, then we will say that AI is related to AJ in the ith power of the relation. Basically, we have to check whether this structure is present in the graph of relation R or not. If this structure is present, then we can say that AI is related to AJ. Now, how do we check this structure? So we focus on the matrix for the relation R and for the matrix of the I minus 1th power of R. And my claim is, to check whether AI is related to AJ or not, it is sufficient to take the Boolean dot product of the ith row of matrix MR and the jth column of the matrix of I minus 1th power of R. This is because if you take the Boolean dot product, this I comma 1 will be multiplied here with the entry 1 comma j, and multiplying here means conjunction, because remember the matrix MR and the matrix M R of I minus 1 both are Boolean matrices. They just say whether something is related to something or not. So I can say that if in my graph the element AI is related to element A1 and R power I minus 1, if any of these n conjunctions hold, then I can say that I comma jth entry, to compute I comma j entry of MR, you need to perform order of n Boolean operations, because you will be performing the dot product of a matrix or dot product of two vectors of size that will take you order of n effort. And how many such I comma j entries are there that I need to compute in the matrix of R power I? There are n square entries, so that's why it will be order of n cube. So now coming back to the naive algorithm, the first step was computing the matrix for the different powers of R, starting from the Boolean matrix of the relative size that will take you order of n. Effort. And how many such I comma j we can compute a matrix for the individual powers of the relation R, or whether so we have this naive algorithm of computing the powers of computing the matrix of different powers will cost me my goal will be to do it with order of n power cube Boolean operations, which we will do in the next lecture. So just to summarize in this lecture,